Okie dokie, diving in okie. The next thing on our list of things to do after enthalpy, which is what we just finished, we're doing entropy. Kind of sounds the same, but it ain't. All right, entropy. Okay, this is symbolized by the letter S. And we are going to calculate changes in entropy. And we put a little knot up there, meaning at standard conditions, 25 degrees Celsius, one atmosphere. So what is entropy compared to enthalpy? Enthalpy is considered the heat content or the heat exchange that goes on when you have a reaction. Is it endothermic? Is it exothermic? Entropy has to do with actually technically what are called microstates. Now microstates, an easier way to put that is, microstates means different variables. But an easier way to put it in more layman's term would be entropy has something to do with disorder, or the lack of order. The more unorganized something is, the higher the entropy. So entropy is analogous to disorder. It's not actually disorder, but for our purposes right now, okay, we'll get into a little bit about microstates later, we'll think about entropy as being disorder. So if you have more disorder, there is more entropy. Second law of thermodynamics. Actually, there are several laws of thermodynamics, hence the second one. The first one is conservation of energy, and so basically energy can't be created or destroyed. There's an equation for that. In Chem 1, we went through that equation with internal energy, but this time we're talking about the second law of thermodynamics in one version. There are many different ways of stating the second law, but one way of stating it is that entropy naturally in a isolated system. An isolated system means no energy can get in and out, and no matter can get in and out. So it's an isolated system. Nothing can get in or out of the system, no matter, no energy. What happens in an isolated system is that entropy always increases, or disorder always increases. Things become more disordered or more unorganized as time goes on. And you do a real kind of simple analogy. It's not a chemistry one, but it's kind of an analogy, and it works, I think, is that you think about, like when I was growing up, I was a teenager, my room was always a mess. And the only way to make it not a mess was to clean it up, and that means do work. I had to do work. Somebody had to work. It wasn't me. It was usually Mom after she got tired of it. But she, I'd go out one day and I'd come back and my room is all clean. And she's like, I cleaned your room. I'm like, no, you just screwed up my organized disorganization. Because I knew where everything was. You know, you had a pile of clothes that needed to be washed. You had a pile of clothes. It didn't need to be washed, but they weren't exactly clean. And you had a pile of clothes you might have just put on and didn't. You get it. Some of you understand what I'm talking about. Anyway, in order to make something more ordered or more organized, work has to be done. It's not going to happen on its own, unless you're Mary Poppins and you can kind of make it clean up on its own, but most of us aren't Mary Poppins, so over time, things become more disorganized. A little bit more of an example for chemistry would be, over time, what happens to iron metal, steel, which is mostly made up of iron. What happens to it over time? It eventually oxidizes. Okay, metals will oxidize over time and become, iron becomes rust. You get iron oxide out of it. And that just happens over time. And after a while, if you leave that iron oxide to the elements, eventually it breaks down and eventually just kind of, goes away. You put your car in a nice, the Rust Belt of the United States and leave it there for 1,000 years and come back 1,000 years later, see what happens to it. It ain't going to be the same car that you left. It's going to be more and more disorganized over time. But that takes a long time. A biological example would be, you, in order to survive, need to eat and drink. If you don't, you die. And when you die, what happens to your nice organized body? It becomes worm food and smelly gases. Because you break down, you decompose. You become less ordered. That's the natural way of things, unless you put work and energy into the system to either make it more organized or keep it organized. So if we want to keep our nice organized body system, and this is, the human is pretty organized, I would think, pretty complex. In order to keep that complexity, we've got to keep putting energy into the system. We've got to put chemical food in, and drink water. Okay, so those are some examples, biology, a little bit of chemistry, one with the iron oxide and one with, just everyday experience. If you don't want something to get unorganized, you gotta put work into it. If you want something which isn't organized to become organized, you gotta put work into it. So the second law says that you cannot have organization or more complex things unless you put work into the system. On their own, things become more disorganized over time. Okay, that's the second law. So a lot of times, sometimes the second law is not stated correctly. People will use it wrong, and they'll say, well, you see, you can't get something which is more organized. You can't get something which is more complex from something which is simple. Simple organisms, 4.5 billion years ago, single-cell organisms couldn't possibly make humans because that's what they must have done. They must have become more and more organized into making us today, and that can't happen. That can happen. Well, it can happen if you have energy going into the system. You need energy going into the system for that to happen. Okay. Yeah. So entropy has something to do with that disorganization. And we will soon see that things want to become more entropic. Things want to become more disorganized, or more, the better word is microstates, meaning more possibilities. Microstates means possibilities. More possibilities of where things can be. And the more things are spread out, the more possibilities there are where things can be, and the more microstates there are. Gases are very disorganized and have many more microstates of where particles can be compared to solids. Solids are pretty darn organized. As a matter of fact, a solid, the definition of a solid, it has to have a crystal form to be a solid. So if you were a quartz crystal, quartz crystals are kind of cool if you haven't seen them, or salt crystals, halite crystals. Those are sodium chloride. And those are nice little cubes. If you have never looked up close and personal at a sodium chloride, all right, a salt grain, do it because it's pretty cool. It's a nice square, cube, square on 3 sides, or 6 sides actually, but 3 sides of my drawing. You will get a perfect cube out of it. That's pretty organized. I think most of us would agree. That's pretty darn organized when it comes to where those molecules are set up. As opposed to liquids, like liquid water, more disorganized, more spread out. Now liquid water has some hydrogen bonding, so there is some connection between the particles, but there is much more dispersity and disorganization as opposed to solid water, which would be the crystal of an ice cube, crystal forming ice cube, which is an hexagonal crystal out of it. That's organized. If water evaporates, it becomes vapor, very disorganized. It's all over the place, wild and crazy. Yeah, okay. So that entropy, we can think about disorganization in terms of states of matter. When you go from solid, that's a very, now this is it's kind of weird. We got to kind of think about how this works. A solid has low entropy. In other words, low disorganization because it's organized, okay? So low entropy means it's organized. It's a little weird, so we've got to think about that. So a solid has low entropy where a gas has high entropy, very all over the place, and a liquid somewhere in between. All right, armed with that information, let's take a look at the next problem on the problem sheet, problem number 4, which says arrange the following substances, so you have 1 mole of each, same amount in terms of particles, in order of increasing entropy. Increasing entropy means increasing disorder. So of these A, B, C, D, and E, which is the most entropic, the most disorganized, and which is the least? And it wants increasing disorganization. Okay, increasing entropy. So increasing entropy means more disorganized. So this is, I'll still use the word disorganized because I think we can relate to that and think about that a little easier than the word entropy or microstates. And organized. Okay, so who is the most organized? Organized means you've got structure, solid, yes, you are, and not, so who has the most organization here? Those are the solids. The solids have the most organization. They're crystal structures to solids. It's pretty darn organized compared to gases. So solids, do we have any solids in this list? Yeah, we do. We've got 2 of them. We have sodium and we have sodium chloride. They're both solids. So I know the sodium and the sodium chloride are going to go to the left because this wants increasing entropy increasing disorder. So here we have more entropy here, less entropy. Okay. So I know the solids are going to go on this side. And do we have any liquids? Because those are, some are going between our gases and our solids. So gases, solids, liquids would be in the middle. I don't have any. Don't have any liquids in this case. Okay, well, I got some gases. In fact, I have 1, 2, 3 gases. And so I know the gases are going to go over this way, and I know the solids are going to go over this way. But I have different gases and different solids. So how do I know which solid is more disorganized or has more entropy? All right, good question. I don't know who asked it, but it was a good question. Okay, here's how you know. The sodium and sodium chloride. The sodium is going to be the least entropic, okay, most organized, least entropic of all of them, including the sodium chloride. Now, why is that? Well, this is where we get into a little bit of microstates, and what I mean by that is how these things are going to be able to have their atoms, or not their atoms, but their electrons moving around, something which is bigger. Sodium chloride is certainly bigger than sodium, so chlorine attached to it. Sodium chloride has more electrons. These electrons can be moving, grooving, shaking, and baking from different energy levels. That's more shifting around, more disorganization, if you will, or I would say microstates. Like I said, microstates is a better word. Microstates means more possibilities, and that's even a better word here. More possibilities for where these particles of this matter can be. And the bigger you are, the more particles you have. The more particles you have, the more they can be in different areas and regions, and therefore there's more possibilities of where those particles can be. The more particles that you have, and the more regions that they can be occupying and moving around, the more disorganized that you are. So with that bottom line, it comes down to is the larger you are, the more entropic you are. So sodium is smaller than sodium chloride, they're both solids, but the sodium being smaller would have less possibilities for its particles of matter to be in certain spots. So the least, that is next in line. Then we have the gases. Now the gases work the same way. There's different gases here. The larger the gas, the more possibilities for those gas particles and the particles within the molecules within the, not just molecules, but the atoms and the electrons making up those molecules where those can be hanging out, moving, grooving, shaking, and baking. So the larger you are, the more entropic, the more possibilities there are for your parts to be in different locations as opposed to more locked in. All right, so what do we have? What are our gases? Which is our largest and smallest gas? Well, the 3 gases I have here are, I've got hydrogen, I've got some sulfur dioxide, and some neon. Hydrogen, we know, is little tiny itsy bitsy, the smallest element in the periodic table. Now I have 2 of them, so what? They're still 2's pretty small, still pretty small. H2 is the smallest. That is going to have, it's only got a couple of electrons there. When you have H2, you have 2 electrons, okay, in this bond, and there's not much they can do. So they're more locked in, there's more organization, less possibilities of where those electrons can be, so we have more organization. Therefore, we have less entropy in the hydrogen. So I'll keep the solids over here in black, we'll put the gases in blue. But these are increasing, remember this is increasing disorganization. So the gases certainly have more disorganization, more possibilities, more entropy than the solids. All right, what do we got next? We've got some sulfur dioxide, I remember that one, and what else did we have? Sulfur dioxide, and neon. Okay, well neon is, it's element number 10 on the periodic table, so it's not that big, and it's just a single neon. It is more entropic than hydrogen because it has 10 electrons and more possibilities for the electrons. So that would go next, and then last but not least would be the larger gas, which is the sulfur dioxide. And sulfur dioxide certainly much bigger, 2 oxygens and a sulfur. Each one of those are bigger than both these combined. So this one is the largest of the gases, the most entropic of the gases. So that would be the order of increasing entropy. We have solids and then gases. We didn't have any liquids in this example, but if we did, those would go in between here. And as we get larger, we get more entropic. So that's why we have the larger of the solids on the right and the largest of the gases also on the right. And that is an introduction to entropy and the first look at entropy and how to apply it to our chemistry.